Hi everyone, my name is Wang. I'm an employee of Ant Group and Alibaba Group, and I'm also doing a postdoc in Peking University. Today my topic is about scaling static taint analysis to industrial SOA applications. Recent years, we have seen an increasing demand for tracking data flows in industry. A typical scenario is detecting data leaks, which happens when private or confidential information is released to an untrusted environment. Let's see an example. Suppose the column ID card in app 1 is marked as private. Any application uses this piece of data directly or indirectly should be regarded as insecure. Here, the data in app 1 is passed to app 2, furtherly reaches app n, saves as ID info column, and finally is shown to users. So a problem is how to identify this long data bus. Another common scenario is about impact analysis. Software changes are inevitable, and we need to clearly know the impacts of code changes. Here is an example. This is a fund trade application. In its recent release, new code is added to open fund accounts. The code seems fine and all tests show no problems. However, the code release happens when the account system is migrating its database. The opening account operation happens on the old database, and the querying account operation happens on the new database. Since there is a delay between the two databases, there is a possibility that an account might not be found. The code change finally causes failed trades and capital loss. So what if we can determine the consequences of the code changes? For example, the code change will add new fund account. We mark it as a high-risk operation, intercept the code release, and require to perform more sophisticated testing so that we may find the bug early. We can also apply it to similar cases such as regression testing of affected interfaces. Then we give an code example for our targeted systems. SOA is a widely used theory for migrating integrating applications. It supports publishing, registering services, and making remote procedure calls. You may find many popular open source SOA implementations. We use the one used in our company as an example. In the figure, app 1 defines a class with the SOA service annotation, claiming that here is a service object. Other applications can refer to it and invokes its methods. The app 2 defines a variable with the annotation SOA reference. It points to the service object in application 1. The app 1 queries data from database, then propagates it through several POGO layers, and according to the remote function call, the data finally arrives at app 2. Specifically, our goal is to find the data flows in precision of fields. In this example, we aim to find these two paths, starting from the ID and name column in database respectively, and insert the ID and name fields of the return value in the service methods. The data may further flow to other applications. We need to connect the paths with them. To do this, many taint analysis tools are proposed, but we still face many challenges. One challenge is the scalability. For an application, its full runtime code includes the application code and the library code such as its dependencies, frameworks, and platform SDKs. If we only count the application code and the dependencies, the size of the jar application is more than 100 megabytes. The number of classes, service methods, and interested fields is also huge. and our company has more than 3,000 such applications. Some scenario requires to scan the application at least one pass per month. Some scenario requires to run analysis for every code release. Thus, we need a highly scalable static taint analysis tools. However, when we try to use available tools, they run too long and consumes too much memory. Another challenge is accuracy, especially in existence of implicit dependencies. One source of implicit dependency is hidden code. For example, the JDK and the dependencies ignored by the Peking profile. Another source is dynamically generated code by frameworks. For example, frameworks may use annotations to inject bins and AOP to insert code somewhere. Such implicit dependency requires handicapped static analysis, or false negatives and false positives occur. There are also implied dependency. For example, when putting the ID and name fields of a DO object into a list, a simple taint propagation model assumes the whole list gets tainted. And furtherly, the container operation such as the stream and the map also assumes that the whole collection is tainted. As a result, two false positive paths are reported. In the following, we give an overview of our approach. The inputs can be source code or bytecode, including the application level code and the dependencies. There is a front-end parser responsible for compiling the code. The parser also takes care of the frameworks and patch simulated code. The distributed scheduler slices a job of analyzing one application into small tasks and run them parallelly. Each task is assigned to a static taint analyzer. The analyzer is built atop of the state-of-the-art tool, FlowDroid, taking advantages of its precision in context, flow, and field sensitivity, and additionally addresses the scalability and accuracy challenges. Then we introduce how we address the scalability challenge. For a baseline static taint analyzer, two main stages are building a core graph so that it can perform inter-procedure analysis, and performing taint propagations so that it can find the taint paths. The job of analyzing one application usually runs on a single machine. In the stage of building a core graph, our observation is that libraries rarely propagate taints, but consumes the majority of the time. Thus, our insight is we can only build the necessary part of a core graph. In the stage of computing taint propagations, we observe that, being context and field sensitive, the main task is exploring the space of the interprocedure control flow graph and the searching for alias. Thus, the key point to reduce the space is pronouncing unrealizable paths and unnecessary alias. At last, the task of analyzing one application may be heavy, and running it in a single machine poses high requirements on memory and CPU. Our solution is slicing the job into small tasks and run them distributedly. In the following, we will introduce how to build the necessary part of core graph and pronouncing unrealizable paths and unnecessary alias, respectively. For core graph construction, the application package is big. Building the core graph for the whole package costs a long time. We observe that The library code accounts for the majority of the application package, but only a small part of them propagates taints. Thus, we construct the library part lazily. Specifically, we eagerly build a call graph for the application code. Then, while analyzing, we resolve the missing edges for a call statement if there are taints reached there, using an existing call graph building algorithm. For pronouncing unrealizable paths, firstly, we explain why there are still unrealizable paths, because we have already used the context sensitivity. The first reason is because there are false edges in the call graph. The second reason is unbalanced flow. For example, when querying data from database, along the control flow from sources to sinks are all returning edges. There is no calling flow encountered yet, and no context is preserved for picking the right call site. In our solution, we record the type information along with the facts. For example, the type of variable this is CB1 here. After returning to this function scope, the equivalent variable of this is CB, and finally, after returning to this function scope, the equivalent variable is CB1, and it should also be in the type of CB1. The types are compatible along this path. However, if we try to return to the right side, the equivalent variable is CB2, and it should also be in type of CB1, while it is in the type of CB2 actually according to this function scope. There is a conflict here, and we pronounce this path. For pronouncing unnecessary alias, the key process of finding alias is like this. It searches backward, going from line 9 to line 3, then go to the called method, returning to line 3, and then go to the line 1 and returning to its calling site. The alias analysis in FlowDroid aggressively searches backward. It slows down the analysis by 5 to 12 times. We use a use-diff analysis to recognize a candidate set of alias and pronounce unnecessary ones. For example, going back into the method getAccount is useless. It has nothing to do with the tainted variable x. It is impossible to find alias there. Imploring line 5 is also useless, because the alias variable empty map is not used in the future. In the following, we introduced how we resolve the accuracy challenge. In the stage of building call graph, we ensure the soundness by using a type-based algorithm to expand the call graph so that there is no missing edges. The precision is improved by pronouncing unrealizable paths as introduced earlier. In the stage of computing taint analysis, we provide a taint propagation model at the precision of access paths. Then we introduce a model. A simple model assumes a collection as an integrity and can introduce false positives. Let's see an example. In line 1, the variable user.id gets tainted. In line 2, one element is assumed to taint the whole collection. In line 3, a collection is assumed to taint all its elements. Thus, the variable alley is tainted. In line 4, the variable alley.name is reported as tainted. However, it is not. In our solution, We provide a model at the precision of access paths. For example, in line 2, we can specify that the first argument of the method taints the value field of the base variable. Thus, the list.value.id is tainted. In line 3, we specify that the value field of the base variable taints the return variable. Thus, ali.id is tainted. Finally, no false positive is reported. In the last, we evaluate our approach. To evaluate its accuracy, we firstly build a micro benchmark containing 37 cases. Some cases are simplified code of real systems, and some are manually created by developers. We compare ANTaint with FlowDroid. FlowDroid is executed under 3 different kinds of core graph construction algorithms. As a result, ANTaint is totally correct, while FlowDroid falls on 53% of the cases in the best circumstances. We also collected a benchmark from real production systems. It contains 60 cases. The figure shows the result. ANTaint is correct for 95% of the cases. FlowDroid is only 13%. Here is the performance result. As the table shows, the average time cost of ANTaint is about 48 seconds, and the memory consumption is about 6 GB. We know that the CHA algorithm infers core edges according to the class hierarchy and doesn't need to maintain a control flow graph. It is very fast and uses little memory, but introducing many false positives. Even though ANTaint costs 65% less time and only 20% more memory than FlowDroid. This is the end of my topic. Please contact me if you have any questions. Thanks for attention.